So today's lecture is going to be discussing two things. So first of all, I want to talk about some properties of integration. So these are things that I probably should have covered last week, but seeing as the lecture was 2.5 hours, I didn't want to make it too much longer than that. So there are just three properties I want to talk about. First of all is linearity, and linearity has two parts to it. If you'll remember, sums also had linearity. So there's the same two parts. We have that constants pull out. So given an integral from a to b of c times f of x with respect to x. So this is the integrand. We call this the integrand. Then I can pull the constant out from the integral. So that means I can pull c outside, integral from a to b of f of x with respect to x. So basically what this means is anything which doesn't have to do with x can be pulled outside the integral. Just like in a sum, anything that doesn't have to do with I can be pulled outside the sum. And the second part of linearity is that given one integral added together, where the integrand is a sum of two functions, I should say, I can split it up, just like in a sum, right? These are built directly from sums, so all the properties that sums follow have to be followed by this. Like this, right? I take each of f of x and g of x and make them the integrand in their own integral. And the bounds stay the same, dx stays the same. Dx has to come along for each of the integrals. Every time you write one of these s's, make sure that you have a dx or a dt or whatever the variable is over here. That's very important. Okay. Another one is, I guess, some sort of a symmetry. I don't really have a name for it, but it's, I guess I should bullet these because that's a little misleading. You can bullet those. Okay. Now, if I have the integral from a to b of f of x with respect to x, I can rewrite this as the negative integral from b to a of f of x with respect to x. So if I flip the bounds, I can correct for it by putting a negative. Okay, so every time I want to flip, I have to put a negative out front. Okay, and I don't know what the official name of that is, but fine. And here's another one which I think algebraically doesn't seem to make all that much sense. It's not obvious from looking at it. But once you think about what the other Nick talked about last week, or this week, with regard to integrals being areas, it's a little bit more clear. So I can rewrite the integral from a to b, and here assuming that a is less than b, so I'm in the interval a to b. If I have a number in the middle called c, then I can split this into the integral from a to c to this some point in the middle somewhere of the same function, plus the integral of the rest of it from c to b. Now again, like I said, maybe this isn't the clearest way to see it, but if you think about them as areas, it makes a lot of sense. Because let's say I have this function here, something like this, and let's say my a is here and my b is here. So I'm looking at calculating this area. Well, if I pick a c, which is in between a and b, let's say right here, Doesn't have to be directly in the middle. It could be really close to A, could be really close to B. And I compute now this integral from here. And then compute this integral, which corresponds to this thing. Then I get the same answer. All this says is that I can compute this integral separately from this and then add them together, and I get the area of the whole thing, which makes sense, right? If I'm looking for an area of a big thing, I can just break it up into smaller pieces and add the areas. Okay, so here's three properties which I should have covered last week, and they're sort of assumed in Nick's lecture on areas, but they're a little bit more rigorous here, so you have them. Okay, so now the second part, the more important part, is something called the fundamental theorem of calculus. And this lecture is going to deal with part one, and Nick will cover, or me, will cover part two next week, because that's sort of a little bit more involved. So there are two parts. And for anybody that has spoken the English language before, you know that fundamental means important because it's such a, it's so integral to the topic. It's I don't even know how to describe it. It's just, it's a fundamental part of this topic. So if you learn one thing in this course, it's got to be the fundamental theorem of calculus. So part one, I'll list both parts here, and then I'll only give examples and stuff about part one. But part one says that if I take the derivative with respect to x of the integral from a to x of a function f of t dt, then I get back f with x plugged in. Now, let's think about what this means. It means that if I take the derivative of an integral, I get back the input. So remember that if I had inverses way back in the beginning of the course, if I had that f of g of x equals x, equals the input, then f is the inverse of g, and vice versa, right? It's that f and g are inverses of each other. What this means is, well, for example, e to the x and ln of x are inverses, right? Plus and minus are inverses, right, etc. These are things which cancel each other out. And it's very intuitive. And these things happen all over the place. We've been dealing with them for the entire semester. Now, the interesting part here, so I'll just say what this means for a second, that derivatives and integrals are, I'm going to put basically in quotes because it's not quite right? I mean, I don't have a t here. It's dependent on what this upper bound is, but it's very close. And you'll see the same sort of a thing happens with FCC part two, are basically inverses. So notice that over here, like plus and minus, when you describe plus, you talk about, okay, well, I'm giving things to a person, or I'm receiving things. Let's say I'm receiving things. I receive 10 apples or something, and then someone takes 5 away. Okay, well, that represents plus 10 minus 5, right? These are very intuitive things, and one is built from the other. Multiplication and division, you think of division as just undoing multiplication. But over here, remember that derivative talks about the slope of a tangent line, right? If I have something like this and I pick a point, then derivative tells me about the slope of this line here. And area tells me about, or I'm sorry, integrals tell me about area under a curve, under a certain, under certain bounds. Now, it turns out that this thing, the slope of the tangent line, and this thing, the area under the curve, which were constructed completely separately from each other and were studied for hundreds of years separately, are actually related in sort of the same way that plus and minus are. That given a derivative, if this was your starting point, you could construct his opposite, his inverse, by just looking at the area under the curve, under certain bounds, which is, I think, just super interesting. It's extremely unintuitive, and this is sort of what turned calculus into a subject on itself. People were doing differential calculus, doing derivatives, and people were doing integral calculus, integrals, for hundreds of years. And then Newton came along and sort of married the two topics, and this is what created calculus as it is. Okay, so this is part one. This is the statement you're going to have to know for fundamental theorem part one. Now part two, I'll give it here, but like I said, we'll talk about it a little bit more later. So this one is, remember, we can do inverses in two different ways. I could do f of g of x or g of f of x. And if they both spit out x, then they are proper inverses of each other. So this is essentially the opposite order. I'm going to do the integral first and then the derivative. Okay, so I want to say the integral from a to b of the derivative of f of t dt. I guess I could use x's here, but that's fine. This is f of b minus f of a, which I'm actually going to write a little bit differently at first, because this is notation that I'm going to be using, or that Nick will be using throughout the next lecture. So this is typically a way to write it. This means that you take f of t, just some variable, and you plug in b first, then you plug in a, and you subtract the two of them. You get f of b minus f of a. So basically, when I take an integral and then a derivative, I guess the way it's written here, it's derivative first and then the integral, but written in this order, I get back essentially the function. The only thing is I have to evaluate it on the endpoints. So it's not quite an inverse, but it's very close to an inverse. Okay, so more on this in next lecture. Which will be coming next week. Okay, so let's return to part one. And let's do some examples. All right. So problems like this are going to look like, it's going to ask you to find the derivative of the integral from, say, -2 to x of, I don't know, let's do a polynomial. T squared plus 2t dt. Okay? And remember how this works. If I have a derivative with respect to some variable, usually written x, and if that x is the top bound in the integral, I can just take the integrand, the thing on the inside, and plug in the top value, the top bound. Okay, so it looks like I have, here's my integrand, I have an x on top, and I have an x down here, the thing that I'm differentiating with respect to. All right, so that says I can just take x and plug it in, and I'm done. So these are pretty easy problems. There's not much in terms of difficulty that we can really throw into these. So let's try another one. go from 3 to p of ln of s. It's not a 5, it's an s. Can't read my own writing. S plus square root of s ds. So notice that I can change the variables in here, I can change the variables out here, and it doesn't really change the problem, right? This t in here is just a dummy variable. The reason I don't want to use x in here is because I'm already using x as a bound, right? X has to do with the derivative. I don't want that to affect my integrand. So when I have something in here, it's going to be a different variable than is out here. So to evaluate this, I have this matching this, and here's my integrand. So I take ln of p plus square root of p, and that's it. Now, there are some sort of different versions that we could do. Sometimes it's not in the proper form. So what if it's not in the proper form? And what do I mean by that? I mean, let's say I have the integral from x to 5, for example, of, I don't know, it doesn't matter, e to the t plus sine of t dt. What if I want to take the derivative with respect to x of this integral? Well, you might want to say it's just e to the x plus sine of x. But remember, I need this and this top bound to match up. And this isn't right, right? 5 is certainly not x. The x is down on the bottom here. So how do I correct this? Well, I use one of my properties. Remember, if I want the bottom bound to become the top bound, here I had a on the bottom, and I wanted it to become a on the top, I just put a negative out front and I flip the bounds. So that's all I have to do here. Same thing works when there are x's involved. I get d dx of the negative integral from 5 to x of e to the t plus sine of t dt. And with derivatives, remember I can pull negatives out because they're linear. So I get the negative derivative of the integral from 5 to x of e to the t plus sine of t dt. And now this is in the proper form, right? I have an x here and an x here. Great. So I get negative e to the x plus sine of x. And that is my final answer. Okay, so let's do an example where your x is on the top, but it's not just x. What do I mean by that? Let's take the derivative of the integral from 2 to x to the 5th of t squared minus 2e to the t. That's terrible. 2e to the t dt. Okay, so it's pretty close, right? Because the x term is on the top bound, and this matches up. The problem is this isn't just x. So what happens here? Well, we have to use chain rule. So in general, here's another way to write the fundamental theorem of calculus, part 1. If I take the derivative with respect to x of the integral from a to g of x, right? This is just some function of x, like x to the 5th, or sine of x, or e to the x, or something with an x involved, but which isn't just x itself, of f of t dt, right? This is very similar to how the fundamental theorem was written before, except there's not just an x in the upper bound, it's a g of x. How do I deal with that? Well, I still take the top bound and I plug it in for t. I get f of g of t, right? So I would just, in this example, take the x to the 5th and plug it in for t. But then because this isn't an x, I have to sort of correct for it. In the same way that when I was taking a derivative, I am taking a derivative, I have to correct for this thing not being an x. I have to take the derivative of, oh, I'm sorry, that shouldn't be of t. Screw that up. That should be of x. I have to take the derivative of the inside. Okay, so in this case, I have my g of x is equal to x to the fifth. So I have x to the fifth squared minus 2e x to the fifth. And this whole thing is going to be multiplied by the derivative of the top bound, 5x to the fourth. And this is our answer in this case. Okay, let's try one more of those. ddq we'll use this time. And we'll go from 4 to the sine of q. And the function will be square root of y minus y squared dy. Okay, so again, it doesn't matter what this variable is as long as it's not the same as what's going on out here. Okay, so I apply chain rule. I take the integrand and I plug in the top bound. Minus sine squared of q. Okay, I have this, but I have to remember to multiply by the derivative of sine of q, which is just cosine of q. And there you have it. Okay, now we can sort of take all this together and use this splitting trick as well in some of our problems, right? This part C. So there's one more example I want to do. And let's do it with the following. Let's go from x squared to, let's say, e to the 2x. Do something a little complicated. And we'll have, I don't know, I'll just pick a polynomial of some kind. T cubed minus the square root of t plus ln of t. Let's do something like that. dt. Okay, this is about the most complicated example that you'll see. All right, so now this problem looks like a derivative of an integral. So that means it should be a problem which involves the fundamental theorem. But it's not quite in the right form again, right? I have a function of x up on top, but I also have a function of x down on bottom. And remember that the statement of these dealt with only a constant being on the bottom, right? A needs to be a constant. And even when we did the chain rule version, I still had a down here as a constant. So I can't have a function of x in the bottom, otherwise this doesn't work right. So how do we deal with a function of x being in the bottom? Well, we use our splitting trick. Pick a value and split. Now, earlier I showed you the splitting trick with integrals. And I said that it had to be the case that c was in between b. Now, in order to see it in this sense, that is true. C has to be between a and b for the integral argument to work. However, this doesn't have to happen. So what does that mean? It means that I can pick any value at all and split this integral. It could be less than a, it could be greater than b, it could be in between. It could be equal to a or b, it doesn't matter. The way that integrals work, the negatives end up canceling each other. So everything works out. So what I can do is, typically, we just pick 0. And this is always possible. You can always pick 0, whether it's in between these two functions or not. So how I'm going to rewrite this is I'm going to split this integral into x squared to 0, the interval x squared to 0 of this same thing. That's a terrible t plus 0 to the upper bound, e to the 2x of this thing. And big parentheses there. So in general, I would say just pick 0. Okay, so I have this piece here, right? Notice we can use linearity of the derivative to do this. Right, remember that derivatives split over addition. So I can use that property to do this. Right. Okay, now this is something I can deal with, right? I have a constant on the bottom and a function of x on the top. This one is pretty close, right? But we've seen examples like this. I have the x function on the bottom and a constant on the top. All right, so I can just flip it. So I pull the negative out. You could just put the negative out here. You don't have to do it in 2 steps like I did last time. 0 to x squared of t cubed minus square root of t plus ln of t dt plus, and I'll just apply it all in one step, meaning I'll just rewrite it this time. T cubed minus square root t plus ln t dt. And now finally, we can apply fundamental theorem, right? Or at least the chain rule version of the fundamental theorem. So I have negative x squared to the third minus square root of x squared plus ln of x squared times 2x, because I have to take into account what's the derivative of the top, plus, and now I have e to the 2x cubed, put this in big set parentheses, minus the square root of e to the 2x plus ln of e to the 2x times the derivative of the top bound, which is 2 e to the 2x. And this is my final answer. And I suppose there are some simplifications I can do in here. But I would say just don't worry about it. If we ask a question like this, it's going to be, do you know the fundamental theorem? And the answer to that should be yes, because again, it's fundamental to the study.